Okay, so yeah, so greetings from Victoria. So welcome to this second to last talk, I think, in the Around the World event in Combinatorics. So we're very happy to have Andrew Suk from the University of California at San Diego. So Andrew got his PhD from NYU in 2011, I believe, supervised by János Pak. He spent a few years after that in some very prestigious postdocs at EPFL in Switzerland, and then an NSF postdoc at MIT. He started, uh, he got his first permanent job at his first, faculty position at the University of Illinois at Chicago in 2014. And since 2017, he's been at UCSD. So we're very happy to have Andrew to speak to us about Turán-type problems for point line incidences. So take it away.
Okay, so thank you. So I'll be talking about Turán-type problems for point line incidences. So this talk is mostly about a project that is joint work with Istvan Tomon and another project that is joint work with Mozhgan Mirzaei. And so I'll start off my talk by recalling the famous Emory-Trotter theorem, which is about points and lines in the plane. So if you have a bunch of points and lines in the plane like this picture here, an incidence is a point line pair where this point P here lies on this line L here. And I'll denote capital I of PL to denote the set of incidences between a point set P and a line set L. And so what the Emory-Trotter theorem says is that any set of n points and m lines in the plane determines at most this many incidences. And if you want to kind of simplify your situation by insisting that the number of points equals the number of lines, then the Emory-Trotter theorem states that any set of n points and n lines in the plane determine at most n to the 4/3 incidences. This n to the 4/3 here is tight by the following example. So just take the n to the 1/3 by n to the 2/3 grid here. So let P be this set of n points here. And then we'll generate roughly n lines with this equation y equals mx plus b, where the slope m will be some integer between 1 and this number here, and b, the y-intercept, will be some integer between 1 and this number over here. And so since m has this many choices, and since b has this many choices, we'll generate roughly n lines. And each of these lines will be incident to n to the 1/3 of these grid points here. Because for each integer x between 1 and n to the 1/3, this quantity here will be an integer that's at most n to the 2/3. So in particular, for each line and for each integer x between 1 and n to the 1/3, our line will hit a grid point. And so since we have roughly n lines, each line is incident to n to the 1/3 points, this construction here will have n to the 4/3 incidences. So this Emory-Trotter theorem over the past 10 to 15 years has received a lot of attention due to its wide range of applications, such as to the sums versus product problem and to the distinct distances problem. And so many people have looked at many variations of the Emory-Trotter theorem. So for example, people are interested in bounding the number of incidences between points and curves in the plane, say bounded degree curves. People are also interested in bounding the number of incidences between points and lines in higher dimensions. Of course, the plane lies in higher dimensions, but you can ask, suppose you have a bunch of points and lines in R3, such that not too many lines lie on a common plane. And then how many incidences could you possibly have? And of course, people are interested in bounding the number of incidences between points in hyperplanes in higher dimensions under certain conditions. But in this talk, I'll just be focusing on points and lines in the plane. And actually, I'll kind of focus on this old question of Erdos, who asked if you do have n points and n lines in the plane, and let's say there are many incidences between them, so on the order of n to the 4/3, then does this arrangement of points and lines show any kind of structure? And in particular, what Erdos was interested in is whether or not this arrangement of points and lines show any kind of grid structure. And so in order to make this question a little bit more concrete, we can rephrase it as a Turán-type problem. So let P naught and L naught be some fixed point line configuration. So if you want, you can just imagine P naught and L naught to be this configuration here, which consists of 4 points and 4 lines. And actually, if I look at the incidence graph of this thing, I get this graph here, which is actually a cycle of length 8, a C8. And then you can ask, suppose you have n points and n lines in the plane, such that it doesn't contain this thing here as a subconfiguration. And what I mean by that is that the incidence graph of these n points and these n lines doesn't contain this graph here as a subgraph. Then how many incidences could you possibly have? So the first time I saw this problem was actually in this book, Research Problems in Discrete Geometry by Brass, Moser, and Pak. And in that book, it's conjectured by shoimoshi that if you do fix a point line arrangement P naught and L naught, then any set of n points and n lines in the plane that doesn't contain this thing as a subconfiguration determines just little o n to the 4/3 incidences. In general, this conjecture is pretty wide open. One of the earliest results towards this conjecture is by shoimoshi himself, who showed that if P naught and L naught is this thing here, this configuration, which consists of 3 points and 3 lines, and actually the incidence graph of this configuration here is this graph here, which is a C6, a cycle of length 6. Then he showed that any set of n points and n lines in the plane that doesn't contain this thing as a subconfiguration does indeed determine just little o n to the 4/3 incidences. And of course, what he actually proved was something more general. So this thing here, the C6, you could think of it as a 1 subdivision of K3. And what shoimoshi actually showed was that if you forbid in the incidence graph a 1 subdivision of the complete graph on K vertices, where K is fixed, then that implies that the number of incidences between n points and n lines with this thing forbidden is just little o n to the 4/3. It's not known if you can still significantly improve this upper bound further. So for example, it's not known if you can improve this upper bound to n to the 4/3 minus epsilon. But kind of interestingly, in joint work with Mozhgan Mirzaei, we were able to get an n to the 4/3 minus epsilon upper bound if we forbid k by k grids. So a k by k grid is basically this configuration here. So it consists of 2 sets of k lines. You can imagine k of them kind of going horizontally, and then another k of them going somewhat vertically. And this configuration also consists of k-squared points, which is at the intersections of the 2 sets of k lines. And what we showed was that any set of n points and n lines in the plane that doesn't contain this k by k grid as a subconfiguration does indeed just, it determines just at most n to the 4/3 minus this quantity here, number of incidences. So indeed, if you do have endpoints and end lines in the plane with many incidences, you should have some kind of grid structure. However, I don't think we really answered Erdős's question, though, because when he wanted to find grids, he also wanted, I believe he also wanted these diagonal lines as well, which unfortunately we weren't able to say anything about. And actually, I won't go into the proof of this result here, but I will just say that the proof of this result is actually a simple adaptation of Shoimoshi's argument. Because actually what this k by k grid here is, in the incidence graph, it's actually just a one subdivision of the complete bipartite graph with k vertices on each side. And so if you just apply that fact and follow Shoimoshi's argument, this is exactly how you get this n to the 4/3 minus epsilon upper bound on the number of incidences. Okay. But in the other direction, so in joint work with Istvan Tomon, we were able to show that there is a set of endpoints and end lines in the plane that doesn't contain a k by k grid and determines at least this many incidences over here. So as you can see, as k gets larger, the number of incidents here approaches n to the 4/3. And this construction here, I do want to talk about in this talk here. But before I sketch this construction here, I wanted to talk about another problem that I've kind of already talked about. So two of the configurations we've looked at are these two here. This thing here just happens to be a C6, and then this thing here just happens to be a C8. And we're trying to bound the number of incidences between endpoints and end lines in the plane whose incidence graph doesn't contain, let's say, a C6. And so you can just think of this as a purely combinatorial problem. And so if we let this extremal number here denote the maximum number of edges in an n vertex graph that is C2k free, then it's a classic result of Erdos, Spani, and Simonovitz that this extremal number here is at most n to the 1 plus 1 over k. And kind of interestingly, this upper bound here is known to be tight for cycles of length 4, 6, and 10. So it's not known to be tight for cycles of length 8, and it's not known to be tight for all the other values of k. And actually, for all of these other values of k, the best known lower bound for this extremal number here are these quantities over here due to Lazebnik, Ustimenko, and Wolder. And determining whether or not this upper bound here is tight for all k, this is one of the oldest open problems in extremal graph theory. However, in this geometric setting, when we're looking at endpoints and end lines and forbidding C2Ks, it was conjectured by Mirzaei, myself, and Verstraete that you can improve this upper bound in this geometric setting. So in particular, any set of endpoints and end lines in the plane whose incidence graph is C2K free determines just little o n to the 1 plus 1 over k incidences. Unfortunately, we weren't able to make any progress towards this conjecture. So this conjecture is wide open. The only case where it's known to be true, well, I guess when k is 2, it's true because of the Emory-Trotter theorem. But when k is 3, it's also true. This is that theorem of shoimoshi that I mentioned earlier. But for all other values of k, it's not known whether or not you can improve this upper bound in this geometric setting here. Okay, so in the other direction though, again, in joint work with Tomon, we were able to come up with constructions of endpoints and end lines in the plane whose incidence graph is C2K free. and determines at least this many incidences here. And as of today, I believe this is currently the best known lower bound for this geometric problem. And this construction here, I do want to talk about, which I believe is the next slide. Okay, so this construction here of endpoints and end lines with many incidences and whose incidence graph is C2K free. It actually starts off with that standard construction that I mentioned at the beginning of the talk, where you take the n to the 1/3 by n to the 2/3 grid. And then you, again, generate those end lines with that equation y equals mx plus b, such that you have on the order of n to the 4/3 incidences. And basically what we observed is that this standard construction here has very few cycles of length 2k. So obviously it has at most n to the 2k cycles of length 2k. The incidence graph between endpoints and end lines is K22 free because no two distinct points contain two distinct lines. And so therefore you can easily conclude that the number of cycles of length 2k would be basically n to the k. But what we were able to show is actually the number of cycles of length 2k in this incidence graph is at most this quantity here, which is tight. And even this little o1, the plus little o1 here is necessary. So why is this true? Well, it basically comes from this keylemma here that says that for any two grid points, P and P prime will have very few common neighbors. So here, common neighbors is in quotes. And so what I mean by that is that there are very few other grid points, Q, with the property that there's a line going through P prime and Q from my line set, and another line from my line set going through P and Q. So in other words, there are very few other points Q with the property that the slope is an integer, and also this slope here is an integer. And to see why that's true, we can fix 2 points, let's say P and P prime. And we can assume for simplicity that P is at the origin and P prime is at this location A comma B. So they're fixed, and so they're in the color red. And we want to count the number of grid points Q with the property that there's a line from my line set going through P prime and Q and P and Q. And the claim is that there should be very few choices for Q. And to see this, we'll determine Q, instead of by the x coordinate and y coordinate, we'll determine Q by fixing a slope and then picking an x coordinate. Because if I fix a slope and an x coordinate, that will determine a unique point in the plane going in this direction. So how many choices do I have for the slope? Well, it's a slope from my line. And remember, all slopes are integers between 1 and this number here. And so basically, there's n to the 1/3 choices for the slope. And so let's fix one of those. And so t here will be the slope of this line, which is now fixed. So a, b, and t are fixed numbers now. And now I claim that the number of choices for u, the x coordinate, is going to be very small. So the claim is that it's just n to the little o1, and then this will prove this keylemma here. Okay, so the way we'll count the number of choices for u, we'll actually count the number of choices for u minus a, this distance here. And this part here won't be very intuitive, but you can easily check it, which is that this distance here, v minus b, will equal to this quantity here. And you'll see why I wrote it out like this in a second. So this isn't very intuitive, but you can easily check it because t is the slope of this red line here. And when I multiply it by u, I get the v. And then the minus ta plus ta cancels off. And then I have the minus b over here. But now if I divide both sides by u minus a, this left-hand side is the slope of this blue line here, which I know is an integer. T is the slope of this line here, which I know is an integer, which means that this last thing over here must be an integer. And so remember, t, a, and b are fixed numbers, and we're counting the number of choices for u minus a. And so given this red fixed number here, ta minus b, how many choices do I have for u minus a? Well, by this observation, whatever I choose for u minus a, it has to divide this fixed number up here. So the number of choices for u minus a will be at most the number of divisors that this fixed number has, ta minus b. And so now I can just use a simple fact from number theory that for any positive integer n, it has very few distinct divisors. So therefore, the number of choices for u minus a will be, so since ta minus b is at most n to the 2/3, the number of divisors that it'll have is at most n to the little o1. And so therefore, the number of choices for u minus a will be at most n to the little o1. And so that's the proof that if you fix any two grid points, there are very few other grid points with this property that there's a line going through P prime and Q and also P and Q. Any questions about that argument or in general? Oops. Okay. Okay, so we have the standard construction of n points and n lines with n to the 4/3 incidences. And we just observed that there are very few cycles of length 2k. And so now all we do is just, and then just to show that there are indeed very few cycles of length 2k, we can apply that keylemma. Because if we do have a cycle of length 2k, we have k of the vertices over here, and then the other k vertices over here. On the left side, for these k vertices, if we just assume k is even, there are n to the k over 2 ways of fixing every other vertex here. And then if I look at two of these vertices, let's say p and p prime, how many choices do I have for this middle vertex q that has the property that there's a line going through P and Q and P prime and Q? Well, this is precisely that keylemma that the number of choices for this vertex Q would be at most n to the 1/3. And since there's k over 2 of them here, we get this quantity here. And then once you fix these k points for the cycle, since the incidence graph is k22 free, that basically determines these k points here up to a constant factor. And so therefore, the number of cycles of length 2k would just be at most n to the 2k over 3. Okay, and so now we have n points, we have n lines, many incidences, very few cycles of length 2k. And now we just apply the standard probabilistic argument, the deletion method, where you just pick a point or a line with a certain probability. You end up with, let's say, capital N points. You'll have very few cycles of length 2k, and then you delete 1 point from each cycle. And then it's not hard to show that the number of incidences between the surviving points and the surviving lines will be at least this quantity here. So that would be the construction of n points and n lines whose incidence graph is C2K free and determines at least this many incidences here. And by basically following the exact same argument where you start off with the standard construction, apply the keylemma to show that there's very few k by k grids, and then apply the probabilistic argument, this is exactly how you get this construction here of n points and n lines that doesn't contain a k by k grid and determines at least this many incidences here. And we talked about other configurations in our paper, but all the proofs are essentially the same, starting with the standard construction and applying the keylemma. And so what I wanted to do now is actually talk about a nice application of these results here to what are called Haase diagrams.
Andrew, I have a hopefully quick question first. About the first result, in the proof of the keylemma, you use the fact that the number of divisors of any integer at most n is at most n to the little o1, and it's like either log n over log n roughly. I guess, yeah, so here. So the average number of divisors is on the order of log n, which is considerably smaller. So if you really care about the little o1, I'm just wondering if you looked into doing this at all, or if you care.
No, yeah, we thought about it, but we wanted to, when we wrote the paper, we wanted to, we thought it was cleaner this way. But yeah, no, I mean, we didn't fight for it so much.
Okay, thanks.
Okay, so so now I'm going to talk about an application of these constructions to what are called Haase diagrams. So given some post set P, the Haase diagram of that post set is a graph G where your vertices are the elements in the post set, and then the edges are pairs of elements that are comparable, but there's no other element Z that's like in the middle here. So you don't have an element Z such that you have this relationship here. And so just as a basic example, here's a post set here with this subset relation. And so the Haase diagram of this post set would be actually this picture here, which is a graph with 6 vertices and 7 edges. And even though these two elements here are comparable, there's no edge between them because of these middle guys here. And so it's an old question that if you do have a Haase diagram, how large could its chromatic number be? So for example, is it true that the chromatic number of every Haase diagram is at most 1,000? You can use a simple fact that I'll talk about later, which is that Haase diagrams are triangle free. And just based on the fact that they are K3 free, you can apply a result of Oshta, Komlush, and Zemuretti to conclude that every n-vertex Haase diagram has chromatic number at most this quantity over here. And actually, I believe this is currently the best known upper bound for the chromatic number of Haase diagrams in general. In the other direction, though, you could take an old construction of Erdos and Heinel known as shift graphs to show that there are, or Haase diagrams do have arbitrarily large chromatic number, so it's not bounded. And in particular, what it shows is that there are Haase diagrams on n vertices with chromatic number at least log n. And then later, Bolabas showed that there are Haase diagrams have arbitrarily large girth and arbitrarily large chromatic number. So in particular, he showed that there are Haase diagrams on n vertices with girth k, and here k is fixed, with chromatic number at least this quantity here. And this lower bound here was recently improved actually by Pak and Tomon to log n. And actually for a while, these were the best known lower bounds for the chromatic number of Haase diagrams. And based on these constructions, some people conjecture that the chromatic number of Haase diagrams should be small. So something like polylog the number of vertices. So some people conjecture that it should be at most, I guess, log to some constant times n, where n is the number of vertices. And if you believe that, then you would at least, assume that it should be subpolynomial in the number of vertices. But kind of interestingly, in joint work with Tomon, we were able to show that these conjectures here are false by showing that there are Haase diagrams with very large chromatic number. So on the order of, that's polynomial in the number of vertices, so n to the 1/4. And also we were able to show that there are Haase diagrams with large girth and also a very large chromatic number. So what I'd like to do in the last, I think, 10 minutes of my talk is basically sketch these constructions. But actually what I like to do is rephrase this problem into another problem about order graphs. So what an order graph is just a graph where your vertices are ordered 1 through n. So you can imagine that they're, on the real line, ordered from left to right. And then the edges are just the edges. They're not ordered in any way. But now that your vertices are ordered from left to right, you can now define what an ordered cycle is. So given an ordered graph, an ordered cycle is a cycle where it starts off with this like monotone increasing path. And then you have one final edge that connects the first and last vertex. And it's not hard to show, actually, that a graph is a Haase diagram if and only if it can be represented as an ordered graph with no ordered cycle. So not only are they triangle free, but you don't have an ordered cycle of any length. And this isn't so hard to show, but I decided to cut the proof out so that I hit the 40-minute mark. So I'll skip the proof. But now that we know that Haase diagrams, or a graph is a Haase diagram exactly when it could be represented as an ordered graph with no ordered cycle, in order to show that there are Haase diagrams with large chromatic number, what we showed is that there are ordered graphs on n vertices with no ordered cycle and with very large chromatic number. And to show this, what we showed is this kind of Ramsey result, which is that there is an ordered graph on n vertices with no ordered cycle with very small independence number. And so once you show this, that implies these results here. Okay. So this construction here kind of, again, it goes back to that standard point line construction that I've been talking about. So again, if you take those endpoints and end lines, where the endpoints is that grid, the n to the 1/3 by n to the 2/3 grid, and then you generate, again, those end lines so that the number of incidences is between P and L is on the order of n to the 4/3. You take this picture and you slightly rotate it so that no 2 points have the same x coordinate. And then basically the construction of this graph is just simply taking the line graph of this incidence graph. So what am I referring to? So we'll define a graph G where the vertices are the incidences between P and L. So in particular, this will be a graph with n to the 4/3 vertices. And we'll order them from left to right on the real line, basically by the x coordinate of the point. And if they have the same x coordinates, that means that they're the same point, because remember I did that rotation. So no 2 points have the same x coordinate. If they have the same x coordinate, that means they're the same point. And in that case, I would order them by the slopes of the line attached to that incidence. Okay, so I have n to the 4/3 vertices ordered from left to right. And then I draw an edge between two vertices if the points are different. So that's the same thing as saying as the x coordinate of p is strictly less than the x coordinate of p prime. The slope of the first line is strictly less than the slope of the second line. And then lastly, the first line, L, goes through the second point, P prime. So basically, I draw an edge between these two vertices if the picture looks exactly like this. And so it's not hard to see that this graph won't have any ordered cycles, because if I have this monotone increasing path, let's say of length 2, because of the way I define my edges, this will force P double prime to lie strictly above the first line L, because P double prime has to lie on L prime. The slope of L prime has to be strictly bigger than L. And moreover, the x coordinate of P double prime has to be to the left of P prime. So you're kind of pushing the points up and to the right. And if this monotone path was even longer, it's not hard to see that that forces, the last point to be kind of more up and to the right of this first line L. And so the point is that you can't have that last edge that connects the first and last vertex, because remember, for that to happen, L has to hit that last point. And by construction, we're forcing that last point to lie strictly above L. Okay, so there's, so we have an ordered graph with no ordered cycle. The number of vertices is n to the 4/3, which we'll just call big N. And the claim is that the independence number is on the order of little n, which will be on the order of big N to the 3/4. And so this would prove, this would be the construction here and prove the theorem. And so to see why the independence number is small, if you have an independent set in this ordered graph, remember these vertices correspond to edges in the incidence graph. So these vertices here corresponds to edges in this incidence graph between P and L. And so how many red edges could you have? So remember, this is an independent set, and basically what that means is that you won't have this Z pattern here. Because if you had this Z pattern here, this vertex and this vertex in G would be adjacent because of this edge here. So L2 hits that second point. And so how many red edges could you have between these endpoints and these end lines if you don't have a Z pattern, this path of length 3? So you can easily show this by induction that there's going to be a vertex of bounded degree. And so in particular, you can easily show that the number of such red edges would be linear in the number of vertices here, which would be little n. And so this shows that the independence number is on the order of little n, which means that it's on the order of big N to the 3/4. And so that's the construction. Any questions so far? So that's the construction of a Haase diagram with very large chromatic number. Instead of taking the standard construction, if you take the construction I showed earlier, if you take the construction I showed earlier of endpoints and end lines, whose incidence graph is C2K free, and with many incidences, then by the same argument, you can show that there are Haase diagrams with large girth and very large chromatic number. And actually, Haase diagrams, they're actually really closely related to disjointness graphs of curves in the plane. So if you have a bunch of curves in the plane, the disjointness graph of these curves is a graph where your vertices are the curves. And then two vertices are adjacent if the corresponding curves are disjoint. And so it's known that there's a close relationship between Haase diagrams and disjointness graphs of curves. And so as another kind of corollary of this result, we show that there is a set of n curves in the plane whose disjointness graph has high girth, and its chromatic number is also quite large. And I just want to say that I thought that this was a bit surprising because I studied intersection graphs a lot. And for intersection graphs, it's well known for several decades that if you do have high girth, then the chromatic number is bounded. And if you have bounded clique number in an intersection graph, then I think the chromatic number is roughly polylog n. So it's pretty small. And so you would suspect that a similar thing would hold for the complement disjointness graphs. But here we show that nothing like that happens actually for disjointness graphs. Okay, so I'm not sure how I'm doing on time, but this is my last slide here. So for me, maybe the most interesting open problem among these problems I talked about is maybe the CA case, because it's not even known in the combinatorial setting, the maximum number of edges in a CA-free graph on n vertices. And so it's not known whether or not we can improve this upper bound in this geometric setting here. Another nice open problem is the C6 free case. So Shoimoshi proved that if you have endpoints and n lines whose incidence graph is C6 free, he showed that you do get this little o n to the 4/3 upper bound, but it's not known if you can get a polynomial improvement on this upper bound or not. So say n to the 4/3 minus an epsilon. And of course, with these Turán-type problems, you can look at all kinds of configurations. I think any result that introduces new ideas or new techniques would be interesting in this direction. So, and then that's it.
Okay, thank you. So if we can unmute ourselves and give a round of applause on the count of 3, 3, 2, 1. Right. Okay, so do we have any questions?
There's a question in the chat.
Yeah, so I can read the question out from the chat. So this is Anurag Bishnoi, and they're asking, is this construction inspired from the constructive lower bounds on Ramsey numbers by Kostochka, Pudlak, and Rodel?
Yes, the line graph. So I believe they first came up, I don't know where the word line graph came from, but it was. So at first we were looking at cliques and then looking at edges between cliques, but then it turns out just edges between edges, which is precisely what they were looking at, was it? So yes.
I guess I have a question. So all of your, so you said this first edge question was, are the things grid-like? And you were looking for grids inside it. I mean, a different interpretation might be, well, the construction looks like a grid. So, and all your constructions were sort of subsets of this grid, right? So could it be something really strong, like anything with order n to the 4/3 edges, really like a positive proportion of it is contained in some thing that really looks like the extremal thing, of only a constant size bigger?
Positive proportion, like linear size.
Yeah, so like a Freiman theorem for whatever for these things. Is there any hope of that?
A positive proportion, like a very large like a linear size subset you're referring to?
Yeah, something like super. I mean, I'm thinking the strongest thing could possibly be true. Is there like an example that shows that no, that's too naive?
Yeah, I don't know. That seems really strong, given that even some small configuration. So I mean, even so, I can't draw it. So if you have that C8, which is 4 lines and then the 4 points at the intersections, and then if you have one diagonal, then nothing's even known for that. So yeah, so once you have the diagonals kind of included, at least there's no techniques known to really improve the little o n to the 4/3. And since we barely know, I guess that's 5 lines and 4 points, to get something really large like a positive proportion, I think would be quite nice, but I have no idea. And in the other direction, I don't know if, yeah, that's too naive or not.
Okay,
I think what Rob thinks is the hope here. I think a lot of people have been working or thinking about this, but as Andrew said, that we're just really, really far from that. So the shoimoshi result uses the triangle removal lemma, and we don't have any proof that doesn't use the triangle removal lemma.
Oh wow. Okay. Fair enough.
Do we have any more questions?
Andrew, there's one big question I think that's still open around these Hasse diagram. So if you restrict yourself to the 2-dimensional posets,
Yeah.
and we've talked about this in the past, I guess, but do you have any insight about this? It's directly related to conflict-free coloring axis parallel rectangles. There's a bunch of papers around this, but
yeah, this is what I think Zegedy, Janos, and some other people were looking at. Yeah, so I think it's the chromatic number. Yeah, I'm not sure. I believe the chromatic number of those were square root of n, I believe. I don't remember, but yeah, I don't have any.
I think the conjecture would be like polylogarithmic. I never believed the original conjecture that for general Hasse diagrams, and there's still some conjectured examples that are still conjectures, but that aren't that for counter examples for that. But this one, I think it's plausible for 2-dimensional that it's only polylogarithmic in n, or at least n to the low 1.
Okay. Yeah, I remember we discussed this a little bit, and then we weren't sure how to determine the dimension of these constructs. We had no idea what the dimension was, and it was kind of clear it wasn't 2. But yeah, I don't have any new insight.
Thanks. Beautiful results.
Okay, any more questions? So if not, let's thank Andrew again for the very nice talk. Okay.